Hey everybody, Mr. Bowman here. This is another video on 3.14 probability distributions. In this video, we're going through all the excellence questions from the 2019 exam. Let's get straight into it with question number 1. So we've got 45% of zucchini plants were able to successfully germinate and grow. 45% of seeds will be able to grow into plants successfully. This year, they're doing... They want to grow at least 6 zucchini plants here. It says the space for a maximum of 10 zucchini plants. 10 zucchini seeds are planted from a few packets. Then the question we've got down here is this is everybody, Mr. Bowman here. In this video, we're looking at all the 3.14 probability distribution questions from the 2019 exam, and we're only going to run through the excellence ones here. So let's have a look at question number 1. So last year, 45% of zucchini seeds planted, they were able to successfully germinate into plants. In this year's garden, it is planned to grow at least 6 zucchini plants. There is space for a maximum of 10 plants if 10 zucchini seeds are planted from a new pack. Question A, and you kind of needed to get I and II both right to get the excellence mark, but use an appropriate distribution model and estimate the probability of at least 6 zucchini plants growing from this year's plantings. So I guess the first thing to note is, this here for me is screaming a binomial distribution. So let's use a binomial distribution. The main reason being is the type of data here, it looks like it's discrete data because you kind of have part of a plant. It's either a plant or not a plant, right? So that means it's discrete data, which means it can only really be continuous or binomial distribution. And I'm liking binomial distribution because of the 2 outcome part of the question. I.e. the seed germinates and grows into a plant, or it does not. So those are the 2 outcomes that we're looking at. So for a binomial distribution, the probability of successfully getting a plant from a seed, the question said it was 0.45. And the number of trials here, we're planting 10 seeds, so any of the 10 seeds could grow into plants, right? So let's draw a number line. I always do these for percent and binomial questions just to help me visualize the question a bit better. So I'm going all the way up to 10 to represent my sample or my number of trials of 10. And the questions asked us, circling it down there, what's the probability of at least 6 zucchini plants growing? So that means if it's 6, 7, 8, 9, or 10, these are the outcomes that we are interested in. The only issue is we can't find that probability. What we've got to do is we've got to find this probability and then subtract it from 1 to get that probability. So the probability that x is going to be equal to or greater than 6, that's going to be equal to 1 minus the probability that x is equal to or less than 5. Putting 5 into my calculator is what I need to do next for my binomial distribution. If you don't know how to do that, do let me know and I can reply with some resources that might help. But when I did that, I got 0.7384 as my probability of 5 or less. And as I said, I've got to take away it from 1 to then get the probability of 6 or more. And when I do that, I get a probability of 0.2616. And that they had a rounding of 4 decimal points. So I've now answered I. Now we've got to get to the II part of it. And that's the discussion-y type part. So to apply the distribution, we've had to make at least one assumption, identify one assumption that may be invalid. So in particular, it wants us to focus on things that are flawed and discuss why it might be the case, and specifically discuss the impact that making the assumption has on your calculation. So we've actually got to link it back to our calculation somehow. So as always, just breaking down the question, thinking about what I want to write is I need to discuss the assumption. So that's the first thing I need to state. I need to state my assumption. I then need to discuss why it might be invalid. And then finally, I need to link to my calculations somehow. So these are the 3 things that I'm looking to follow here. So firstly, the assumption I've made is binomial distribution always assumes independence. The idea that one seed is going to be independent, or it's not really going to impact the next seed that's happening. So our calculations, or that I've definitely not spelled calculations right, our calculations have assumed that each zucchini seed germinating and growing is independent of the other seeds. So that's the assumption that we've made. And I think straight away we know that's probably going to be a bad assumption because, for example, if the soil conditions are good, if they're well watered and well cared for by the garden owner, and if the weather conditions are good, that probably means all of them have a better chance of growing. And if none of those are present, so there's poor gardening, the weather's awful, probably means it's less likely. So the idea that these seeds are independent of each other really is bad because they're sharing the same garden and they're all going to be impacted by the same variables. So they're probably not independent of each other as a result. So that's what I'm going to do here. I'm going to discuss why it's invalid next. So these seedlings are all from the same garden and will be subject to the same gardener and the same weather conditions. This means they are unlikely to be independent. Full stop. So I've got that part there. Let's now, just to move room, let's move my kind of stuff over here. We now need to link to calculations. And without the linking part, you can't get your excellences marks, unfortunately. I know a lot of people get annoyed when they do all this lovely, nice conversations here, but ultimately you're trying to explain how it relates to your calculations, so you need to mention your calculations. So the calculations we've got here related to onto 6 seedlings. So let's talk about the weather part of it. So if the weather conditions are good and conducive, I spelled conducive wrong, for zucchinis to germinate and grow, then the estimate in I, so that was the one we calculated above, may be an underestimate. So that's my link. So the fact I'm said it's an underestimate, that's my link to the calculation. So if the weather's really, really good, I know the number I've calculated here is probably going to be on the lower side, and the actual probability of getting 6 or more might be a bit higher. And I do need to recognize, and the vice versa happens. If the weather's conditions are really, really bad, I know this might actually be an overestimate. So I'm going to write, and vice versa if the weather is not conducive. There we go. So that wraps up this question. Hopefully you can see how I process it. Talked about my assumptions, discussed why they were invalid, and then I made a clear link back to my calculations. Okay, we are now on to question number 2, and similar theme with the zucchinis. We've said zucchinis are picked when they are more than 190 millimeters long, but before they grow over to 270. So straight away for me, that sounds like that's going to be a minimum, and that there's going to be a maximum. So maybe this is going to be a triangular or a uniform distribution question. Let's see. The most common length is 220. So that's really good. Most common, that's your mode, which is the peak. So that probably confirms it's going to be a triangular distribution type model. So let's sketch that out before I read the rest of the question. So there's my x-axis, there's my peak. So as I said, they've got to be picked when they're 190. They can't go for more than 270, and down the middle, we've got a peak of 220. So zucchinis, small zucchinis, which are less than 215, are preferred for eating. So let's draw that on my axis. So let's draw 215 here. Not to scale. So these are the preferred ones. Calculate an estimate for the probability that at most 5 of the next 10 zucchinis are picked that are small. Okay. Clearly identify your choice of a distribution, associated parameters, and state any assumptions. Okay, so this one here is actually going to be quite tough. So what we're going to do is we're going to use the triangular distribution to find the probability that x is smaller than 215. So it's definitely going to be a triangular distribution here. Now, once we've got that, we then need to do a binomial distribution model to then figure out the probability that at most 5 of the next 10 zucchinis are happening. So this is kind of like I always call this like the inception of probability questions for my class. It's kind of like a distribution within a distribution type question. So we're going to use the triangular distribution to find out the probability of it being a small zucchini. And then after that, we're going to use a binomial distribution to find the at most 5 of the next 10 part of the question. Okay, so let's shade in this bit here. That's the area that we're ultimately trying to calculate here. And I guess the first part is it says clearly state the choice of your model and the parameters. So I guess even though it's evident by the drawing, the triangular distribution is what we're using here. And our parameters are a value, which is our minimum, is equal to 190. Our b value, which is our maximum, is equal to 270. And our c value is 220. That's our mode. I should write that there, mode. So I guess the key part of this question is trying to find the height at this particular point here. And you'll have a formula sheet that gives you all this information. But in our case, the height when x is equal to 215, and this is from the formula sheet for the left-hand slope stuff, the height is going to be calculated by 2 times x minus a, whatever that is, and then we're going to do in the next bracket b minus a, and then we've got c minus a. So just a reminder, all of that is a direct copy paste from the formula sheet. I'm now going to calculate what that is. So remember, we've got a and b, and then c is in the middle, and then x is that 215 over there. So let's just kind of maybe write that next to it. So there's my a, there's my b, there's my c, and over there's my x. So 2, and then we've got x minus a. So x minus a is going to be 25. So it's going to be 2 times 25 as my numerator. And then b minus a. So b minus a is going to be 80. And that's going to be times c minus a, which is 30. And when I plug that into my calculator, I get 1 over 48. And that was the fraction. So I've now got the height. So I now need to think about the actual probability, which is what I'm using the triangular distribution for. So the probability that we're having a small zucchini, that's equal to the probability that x, being the length, is less than 215. And because it's a triangle, that's just going to be 1/2 times base times height. So the 1/2 part ain't going to change. The base of this triangle is the difference between 215 and 90, or 190, and that's going to be 25. And the height of my triangle, I've just calculated to be 1 over 48. So I've got 1 over 48 there. Looking pretty messy, but I'm just going to bang that into my calculator, and I'm getting 0.2604, and that there had a 4 decimal point rounding. Okay, now that I've got that, this here is actually going to be the probability of a successful outcome in terms of my binomial distribution, and a successful outcome being the probability of being a small one. So the next part of my question is I need to calculate the estimate for the probability of there being at most 5 of the next 10 zucchinis picked are small. So I'm now going to revert or switch back over to a binomial distribution. And my parameters, I've got n is equal to 10 trials because I'm picking 10 different zucchinis and I'm trying to figure out if they're the small ones or not the small ones. Don't forget, I've got 2 outcomes, small or not small, so that kind of confirms my use of a binomial distribution. My other parameter is the individual probability of success, and we've got that from our triangular distribution to be 0.2604. We've now just got to figure out what we're trying to do. So let's draw my number line, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we're trying to find the probability that at most 5. So at most 5 would be any of these kind of outcomes over here. And we're not really interested in 6 or more at this stage here. So for this group, the parameter, or x, is going to be equal to 5 for my normal distribution calculator. And again, if you don't know how to do this, do let me know in the comments. I can reply with some videos. I'm pretty sure I made some of me of showing you how the calculator works at some point. So anyway, the probability of that happening, so the probability that x is being less than or equal to 5, when I put that on my calculator, is going to be equal to 0.9759. So that means about 97-98% of the time, I am going to get 5 or at most 5 cucumbers. So I've done most of the question, so there's actually heaps to it. So I've done the triangular part. I've used that to help me with the binomial part. And going back to the question, I've just got to state any assumption made. So the big assumption here with binomial distribution, and to be honest, it's maybe 8 out of 10 assumption related questions you're going to get in this exam or concepts is going to be about independence. So we've assumed that the length of one zucchini is going to be independent from the next zucchini, which may or may not be a valid assumption. So as part of our calculation is what I'm going to write. As part of our calculation, we have assumed that the length of one zucchini, the length of one zucchini is independent from the length of the other zucchinis. So that wraps up this question. Just noting, we haven't been asked to critique the assumption. All it really has asked us is to state it. So we don't need to critique why that's a good or bad assumption here. But be careful to read the question, because sometimes you are asked to discuss the validity or if there are any issues with the assumptions. But here we weren't. We are now on to question number 3, and this is carrying on with that corn-related theme from the previous question. So we got data from last year's super sweet corn. So key thing to note, this is data, so this is kind of like actual things. We've got data from 62 corn cobs, and the distribution of the data is drawn down below. For this data, we know the mean, so we're given a mean. We know the standard deviation. And we also know that it's claimed that over 10% of that. Okay, so question down the bottom here says, justify the use of a normal distribution model. Support your answer with statistical reasoning. And really important down the bottom, it describes what it wants you to do is we need to describe at least 2 features of the distribution. And we need to include at least one calculation as part of our discussion. So just a reminder, so we're looking for 2 features. And we need a calculation. So as always, I kind of think about what I want my response to look like before I do that. So for me, the biggest and most obvious thing is a normal distribution has to have symmetry. So I'm probably going to want to talk about symmetry as part of my conversation. And the second thing, it could be unimodal or the fact that it's bell-shaped. So that kind of discussion, it could be bell-shaped and unimodal. So I think those combined kind of necessitate the requirements of a normal distribution model. And then finally, just a reminder, it did ask us to do some calculations as well. So we're going to sit down there and do some calculations to see. So that's kind of the rough scaffolding of what my answer is going to look like. And when we're answering these, it's really important to note we're comparing a theoretical bell curve with the data we've got, so we have to make the comparison. So I'm going to start off with a normal distribution is symmetrical. So that's starting with what a normal distribution would look like. And then I'm going to go into our distribution of yield per cob for all super sweet corn appears to be symmetrical through the line y equals 152.5. So I'll explain what that means. So basically that line y equals 152.5, that's basically down the middle. So you see how we've got three chunks kind of all in the middle. The middle one is in between 150 and 155. So the middle of that is going to be 152.5. But it does look like there's an element of symmetry. The left-hand side of the graph is roughly the same as the right-hand side of the graph. And I always like to use some statistical evidence or some kind of number from the graph as part of my answer to make sure I'm doing that. I've stated what a normal distribution should look like. I've stated what our graph or our distribution looks like, and now I can make the comparison to confirm what it might suggest. So this suggests the normal distribution and our distribution both have elements of symmetry. I've now linked together the two distributions, the normal one and the distribution that we have here. I'm now into the second part of the comparison that I need to make, and I'm going to do a similar thing to the first one. Is I'm going to discuss what the normal distribution looks like, and then I want to discuss how our distribution looks like, and then finally I want to make a comparative statement about the two distributions. So let's get into this. So a normal distribution is bell-shaped. Oh gosh, sure. There you go, bell-shaped and unimodal. I now want to talk about our distribution and whether or not it has those elements as well. For our distribution, we can see a large, or we can see the majority of data centrally located between 145 grams and 155 grams. And that's what you'd expect in a bell curve, right? You've got most of the data in the middle, and then there's a smaller, less frequent amount on the tails. We can also see lesser amounts of data on the left and right hand tails. This suggests our distribution is also bell-shaped. Bell-shaped, and I'm going to say like a normal distribution. Okay, so I've done the bell-shaped part. I probably want to mention the peak, and there's the unimodal, the peak. There's not too much to probably mention here, because I have mentioned it here, and I've actually just mentioned that incorrectly, shouldn't it? That should be to 160. So let's add in a little comment here, which is the peak, confirming it is unimodal. There you go. So I've added in all my comments. I've got some grammar type stuff here, but I'll ignore those. And the last thing it wants us to do as part of this calculation is to do some actual calculations. So we've been given the mean and the standard deviation, 152.3 and 7 grams. And we've got the raw data. Let's make a comparative calculation just to check if it's actually relevant. So, let's, for example, let's calculate the probability of less than 145. So you see this gap here, 145. So if it's a normal distribution, this observed data should be roughly the same as the probability from the normal distribution model. For example, under the normal distribution model, and I'm going to write mean equals 152.3, and then standard deviation, what was that, 7 grams. We have a probability of, so the probability that x is less than 145, I said it was, and that's going to be equal to 0.1458, and it had a 4 dp rounding. Okay, so that was the normal distribution model, and I've used the graphics calculator to get all of those numbers. I now want to check, using the actual data, what would the distribution come up with? So we can kind of see here, this first kind of bar in our bar graph here, it's got 3, and the second bar has 5. So that means there's a total of 8 people, or 8 corn, that were less than 145. And that was 8 out of 62. So from our distribution, we know that the probability is going to be 8 out of 62. From our distribution, we know that Px less than 145 is going to be equal to, as I said, 8 over 62. And when you calculate that as a decimal, we're going to get 0.1290, also with a 4 dp rounding. And we can see these numbers, they're actually pretty similar. They're about 1.5% off, which we expect the theoretical model to be slightly different to the actual data, but we're really, really happy with that number. Okay, so going back to what's required of me, I've described 2 features. I've talked about the symmetry and I've talked about the bell shape and the unimodal shape of our graph. I've done some calculations like it asked me, and now the very final step, let's draw some kind of conclusion. So based on the 2 features I discussed, based on the calculation I performed, do I think a normal distribution model is appropriate for this super sweet corn crop? And I think absolutely it is here. As our distribution was symmetrical, bell shaped, unimodal, with a consistent probability, I think that the super sweet corn crop can be modeled by a normal distribution. There you go. So I've wrapped up this question, and I know I've talked a lot about this question. I've spent nearly 9 minutes on it. I just want to note, as I was talking about it, just to note, I was using these numbers. See how I got 152.5, 145, 160, 145 over here. I was using numbers back in that. So without the use of numbers, sometimes you're not going to get these marks. We are now on to question number 4, and this carries on with that corn theme again. You might have seen these in the merit questions earlier. So we've got a normal distribution model for the super sweet corn. That was the mixture or the brand we had earlier. There's a new type called Ambrosia sweet. Hopefully I'm saying that right. The data below, blah, 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 grams per kernel can be modeled by a normal distribution as well. The normal distribution for the Ambrosia sweet is mean of 149 and a standard deviation of 7. Remember from the previous question for the super sweet, it had a mean of 152.3 and it had a standard deviation of 7. So just noting that might be relevant for later. And the question basically, I should note the blue one is the super sweet corn from the previous question, and the red one is the new Ambrosia super corn or super sweet corn, whatever it's called, for the new question. So that's the new type they've added. So we've been asked to compare the distribution models for the super sweet brand and the Ambrosia sweet brand. Okay, so as always, this is just a big wordy question. We've got to plan what we're trying to say. And we've been asked to compare the two, and ultimately there's only 2 things we really can compare between the distribution models. The first thing is the mean. We can compare the means, and then we can compare the standard deviations. So those are going to be my 2 kind of sources of comparison. So the mean ones are quite a nice, easy comparison. All we can really say is the mean for one is bigger than the mean for the other, which means on average it's going to produce more corn per cob, etc. So by looking at our numbers, we can see the new type, the Ambrosia kinds, that's got a mean of 149. So that's the red one here. So that's why you can see the peak of the red one is is further back than the peak of the blue one. And that's because the mean for the super sweet, the blue corn, is higher. So we're expecting it to be more right than the red graph there. So that's basically what we're going to talk about. We're going to talk about that mean, comparing it. So the difference between them is roughly 3.3 difference? So we've got 152.3 minus 159 gives you a difference of 1 or 3.3. So let's start talking about that. So the distribution for super sweet corn yield per cob. Noticing I'm using all of the terminology yield per cob that the question has because I want to incorporate as much context as I can into my answer to help me convince the marker to give me that mark. So the mean for that, so it has a mean of 152.3 grams, which is slightly larger than the mean yield per cob of the ambrosia sweet corn of 149 grams. So that's me just stating the means for each of the two types. And I've made it comparative. I've said it's slightly larger. That's my comparison that I'm aiming for. So now let's just quantify it. So let's talk about the 3.3 grams. So maybe we'll just write in brackets here, difference of 3.3 grams. So what does this mean? So this means the super sweet corn, on average, will produce more corn per cob than the ambrosia sweet corn. And that's basically what we're trying to say here. So this tells us that the super sweet corn will produce more corn per cob than ambrosia sweet corn. And I'm just going to write in brackets on average because that is an average at the end of the day. And we can see, there is a bit of variation. So some of the ambrosia corn will be larger than some of the super sweet corn. Okay, so that's the mean conversation. Let's now think about the standard deviation one. And again, we're going to start off with the usual deal, just like we did before, just a comparison of the numbers. So we can see the standard deviation for the for the ambrosia sweet corn is 4. That's the red graph. And the standard deviation for the super sweet corn is 7. So because the blue one has a standard deviation of 7, that's why we can see it's much more wide. So that normal distribution graph is a lot wider than the red graph, which is a lot narrower and a lot taller. So that kind of explains a lot of what we're seeing here. So let's start off by talking about the numbers, and then maybe later on we can talk about a bit more to it. So the distribution for super sweet corn yield per cob has a standard deviation of 7 grams, which is much larger. So last time I said it was slightly larger. There it is, slightly larger. This time here, the difference between 3 and 7, that's quite a big difference. So that's much larger instead of slightly larger. So much larger than the standard deviation of 4 grams for the ambrosia sweet corn variety. So that's the first thing. I'm just really stating the numbers. I now want to talk about kind of what that means. So before we said the mean told us that one is slightly bigger on average than the other in terms of the yield. Now this one here, the standard deviation talks about the variation or the spread of the corn. So it tells us that the ambrosia corn, because it's a lot narrower, that red graph, it's a lot more consistent in terms of the yield per corn than the super sweet corn, which is that really wide blue graph. So it means it can take on some really big yields, but it also has a lot of really small yields over here. So that consistency is kind of the difference between the two graphs here. So this tells us that the yield per cob of ambrosia sweet corn is more consistent than the yield per corn for the super sweet corn. And I probably want to explain this one in a bit more detail, linking it back to what I mentioned before. So you can see most of the big corn is from the super sweet one. And that makes sense because on average they're bigger. But if you look down at the other side, you can see, the blue line is ahead of the red line down the bottom there. So that means the small corn, most of the small corn is also from the super sweet brand. So you can kind of see it's a bit of a double-edged sword because of this variation. So the difference in standard deviation explains why we see the higher yield per cob being the super sweet corn variety. However, we also see that there are more cobs with a smaller yield from the super super sweet corn variety. So that's a bit interesting. That's kind of the opposite of what we were saying before. And we probably want to carry on because we can see the small corn and the big corn are all dominated by the super sweet corn. So those middle ones, that big chunk in the middle is dominated by the ambrosia one. So most of the middle weighted corns per yield per corn or whatever it was is there. Whereas we can see the middle yield per corn being dominated by the ambrosia sweet corn variety. There you go. Jeez, forgive my bad spelling as we're doing that. To fix a few. Okay, we are now on to question number 5. So the mean number of weeds plants per square meter. So keyword per. Don't forget that's normally a giveaway that you want to use a percent distribution. So the mean is 6. Use an appropriate distribution model. Calculate an estimate that at least 4 weeds will be found in each of the next 5 square meters. So there's going to be 2 parts to our calculation. The first part is we're going to need to find the probability of 1 square meter having at least 4 weeds. And then once we've got that, we can then think about how that relates to 5 square meters. But let's figure that out first. So I guess the first thing to note is I am going to be using a percent distribution. So it's always important to state down the distribution you're using and the parameters that you're going to be inputting as well. So the parameters percent distribution really only has the mean to worry about. So our parameter lambda is equal to 6 in this case here. So let's draw my number line to help me process the question. So I've got 1, 2, 3, 4, 5, 6, 7, 8. And it could go on a bit more. There could be heaps and heaps of weeds in a particular square meter. And we've been asked to find the probability that a square meter has at least 4. So that's going to be 4 or more. So we're looking for this chunk up here. Reminder that the percent distribution, it only really works from left to right. So what we're going to need to do is we're going to need to find the probability of this chunk here. And we're going to have to go 1 minus that probability to then find the probability of this chunk up here. So I guess to get a bit more mathy with it, so the probability that x is equal to or greater than 4, that's going to be equal to 1 minus the probability that x is equal to or less than 3. So that's basically saying, this group is going to be equal to 1 minus this group. So we then plugged it into our calculator. So that's going to be 1 minus, hopefully for this, if you've got x equals 3 and lambda equals 6, hopefully you're getting 0.15120. And when I do that subtraction, I'm getting 0.8488. And that ultimately was run into a 4DP type number. So that's the probability of 1 square meter. So I've now got 1 square meter sorted, but the question, or the next part of the question that I've circled just then, that relates to, well, what if I've got 5 of these square meters? What's the probability that all of them have 4 or more weeds? So what's the probability that all of these have 4 or more weeds in it? So that's what we're moving on to now. So I guess in terms of our notation, we're going to go the probability that x is equal to or larger than 4 in all 5 meters squared. That's just going to be this number here to the power of 5. So it's going to be 0.8488 to the power of 5. And when I plug that into my calculator, hopefully you're getting 0.4406. And again, that there was a 4DP rounding. So I've done the math part of this, and that related to I, and you did need, unfortunately, both of them to get the excellence mark here. So consider any assumption you made in your calculation, and discuss whether or not this is likely to be valid. We're going to type up our answer here, and just a reminder, the nice thing about these assumption type questions is if you're really stuck, probably 8 out of 10 times, if you talk about independence and link it to the context of the question, you're probably going to get some marks for it. And in this case, it was all about independence, so you'd actually get the full excellence mark for it. So the calculations above, calculations assumed that the number of weeds in each of the separate square meters. So remember, we had 5 square meters, and we've done a calculation for each 5 of these. So by timesing them all together, we've assumed that each square is independent or unimpacted by another square. So that's the assumption we've made. We've assumed they are independent of each other, that one square is not going to impact the weeds in the next square. So we've assumed that the number of weeds in each of the separate square meters is independent from the other square meters. So I personally think, let's say you're in a garden and all of these square meters are physically right next to each other. It makes total sense that the weeds will pop up in one of the square meters, and then they might grow and spread to the next one, and then grow and spread to the one after that, and then that, and then that. And that's what's going to happen if they're all next to each other. If it's a huge garden and they're all really far away from it, and you've got one square up here, one square in the other corner of the garden, those two gardens, or those 2 square meters, are probably independent of each other. But if they're right next to each other, no way they're independent. If there's weeds in one, that's probably going to increase the chance that there are weeds in another. And vice versa, if there's no weeds in one of them, that probably means the next one's less likely to get weeds as well. So we want to talk about that idea that if they're next to each other, the weeds are going to be impacting the other square meters, probably means we don't have that assumption of independence that we need. So this assumption may not be valid. And noticing valid, I do this deliberately. They've used the word valid in the question. So I make a point of picking out those keywords and using them as part of my sentence as well. So I'm trying to draw on what the question's asked. So it may not be valid if the 5 plots are next to each other, as we discussed, then the weeds may spread in between the plots. This means the number of weeds in each of the 5 plots may not be independent of, not on each other, of each other. So that was a really nice question. The math itself was pretty cruisy, I think, in terms of excellence questions, and backing it up with these assumptions about independence is how we converted that to an E. And just a reminder, if you've got an assumption or you've got to talk about something and you're not sure what to talk about, there's a really good chance if you start talking about independence, you're going to get some really good marks from it. Okay, and we've got question 6, which is the final question or final excellence question from the 2019 exam. If you're looking for other excellence questions, do check out the quick maths link that I put in the bio to this one. There is a link to heaps of other excellence questions if you want to look at them. So we've got some organic weed killer. It's attempting to reduce the number of weeds in the garden. That's really important for this particular question. The plot below, so this is the plot they're talking about. Basically, it's just a graph, and it's the observed data from 30 separate 1 square meter areas. And key thing to note is after the weed killer was used. The mean number of weeds per garden was known to be 6. That was from the previous question, so I'm guessing that was before the weed killer was used. The weed killer manufacturer states that the weed killer can achieve reductions of up to 40%. Based on the data provided, can you conclude that the weed reduction rate for the new weed killer was at least 40%? So what this question I'm guessing is us to do is we're going to use our expectation algebra to find the mean of our data from all the information in the plot. We're then probably going to do 6 minus the 40%, and We're then going to compare the two numbers. If the weed killer's done a really good job saying it's at least or above 40%, then it's going to be noticeable in the data that we've done. So let's calculate the expected value, or the mean is probably our starting point. So remember that the mean is equal to the expected value. And it's going to get a bit messy, this one here. So basically, there was one weed here, and that happened 1 out of the 30 times, noticing that there's 30 there. So this one here is going to be 1 times 1 out of 30. We then got 2, and that's 5. So it's going to be, we're going to add on 2 times, and then don't forget that was 5 out of 30. And then we're going to do the same for 3. So 3 was from down there, and that was 6 out of the 30 times. So we've got 6 out of 30. We're then going to add on the 4 contribution to the mean. So that's 7 out of 30. So that's 4 times 7 out of 30. And we're then going to add on, we're on to 5. So that's 5 out of 30 there. So that will be 5 times 5 out of 30. And we're then going to add on the stuff for 6. So 6, that's 3 out of 30. And then we're going to be adding on 7. So 7, 8, and 10 all appear to be 1 out of 30. So that'll make our life a bit easier. So it's going to be 7 times 1 out of 30. We're then going to add on 8 times 1 over 30. And then we're going to add on the 10 times 1 over 30. And we don't have to worry about the 9 or the 10 because that would have been 0 out of 30, which of course would have been 0, and anything times 0 just kind of goes away. So I've got that. It's quite messy, but once I've done all of that, that gets me to 125 divided by 30, which was 4.1667, and that had a 4 dp rounding. So this was the new mean number of weeds per meter squared after we did all the weed killing. So I now want to compare that with what would have happened if the manufacturer's reduction of 40% said. So let's write manufacturer's claim. And that's going to be the mean based on this. I've written a y there, but the mean is going to be, it's going to be 6 times 0.6, isn't it? And that there would have been 3.6. So we can see there's quite the difference between the mean we're expecting, 3.6, with the mean that's actually happened after we've applied the weed killers. Okay, so thinking of the question, remember the question says, can you conclude that the weed reduction rate for the new weed killer is at least 40%? We cannot, because if it was at least 40%, the actual mean should be below or equal to this 3.6. So it's actually quite above, which means the weed reduction rate was much less than 40%. So let's start talking about that. So if the claimed 40% reduction in weeds is valid, we would have expected the average to drop from 6 to 3.6 or less. So that's what I was talking about. That's that 3.6 number. So let's now actually answer the question. Because the new mean is 4.1667 weeds per square meter, we can conclude there was not a reduction of at least 40%. Forgive my bad spelling there, but that was meant to be conclude. So I think that wraps up this questionnaire. That was actually a really nice, easy excellence question, maybe one of the easiest ones we've seen in this exam, but hopefully you found them useful. So don't forget to check out the link in the bio. There's heaps more excellence questions and the achieved merit stuff if you want to have a look. I'll be slowly making out more and more videos, so keep an eye out for them, and hopefully you find them useful for your exam revision.